anyways, we'll talk about the more detail today. Is Darvin's not here. Okay. Let me remind you that there's a progress report due on your final project this Friday, and I would say for the first week you ought to be able to summarize the final project in a paragraph or so, and block diagram of the software, the hardware, how you think it's all going to fit together. Are you going to use NIOSes, or are you going to use pancake processors? You're going to roll your own. How are you going to do it? So about between a paragraph and a page, I would say would be right for this progress report, and it should be a fairly high level thing, because I doubt if any of you have really started coding very much yet. When do you want those, Darvin? Sunrise Friday? Before lab? All right, Sunrise Friday. That way you can work on it all night. I hope you don't do that. Excuse my voice. I seem to have round 2 of whatever the cold is that's going around. I'm getting a little tired of this, but oh well. I want to talk about sound synthesis today, particularly what might be called special effects or music synthesis. And as I mentioned last time, I'm going to talk about at least 3 different techniques. The signal noise ratio on this board is terrible. Spectral matching, which we started talking about. So-called empirical, particularly FM synthesis. And third, physical synthesis. I'm not going to talk too much about subtractive synthesis. Spectral matching you might call additive synthesis, because what you're going to do, what you would do in this case, is to take a series of frequency components and add them together. Subtractive synthesis would be that you start with a broadband signal, which could be white noise or it could be pulses of some sort, and then you filter out some of the signal. And if you were going to synthesize voice from first principles, that's what you'd do, but I'm not going to talk about synthesizing voice. So for spectral matching, as I said last time, for additive, what we want to do is we want to come up with some sort of compact scheme for producing a sum I equals 1 to some n, or typically n here would be 4 or 5, but not 10 or 20 harmonics, and with some gain times some sort of amplitude modulation, typically of a shape that has some sort of rise and fall. So AI of t is going to be modeled as some e to the, well, let's see, what do we want to, how do we want to say this? We want a function which goes like this, multiplied by a function that goes like this, so that we get some sort of rise and fall. Looks like this. So we want some fall time e to the minus t over tau fall times 1 minus e to the minus t over tau rise. And t rise and t fall are going to be different for each different harmonic. So I suppose it has to be T fall I and T rise I. The time constants are going to be different because the different harmonics are going to decay at different rates. Now, as mentioned last time, you really don't want to, well, you could have a lookup table of exponentials, or you could do a Taylor series expansion to calculate exponentials, or you could do some other scheme. But the easiest thing to do to generate exponentials on FPGA is just calculate a version of the differential equation for generating first order differential equation for generating the exponential. So what works quite well is you in some system, in some number system, you initialize some amplitude of rise to some sort of max integer or max value or some fairly large number, and we're doing this all in integer format. So you want some large integer with lots of bits that you can then play with, and then at every time step, so this is the init, and then at every time step you just set amp rise equal to amp rise minus amp rise shifted by some rate parameter. And so the rate parameter then is going to be an integer from 1 to 10 or so, and is going to represent factors of 2 change in the time constant. Right? So you're only going to be able to set the time constant within a factor of 2, but on the other hand, it only costs you a shift to do the calculation. So at every time step, you iteratively calculate a new value, and this is exponential because you're subtracting from the current state, you're subtracting off a small portion of the current state. And if you play around with the differential equation, you'll see that that's a very truncated but reasonable approximation of a finite difference equation, which matches the finite differential, the differential equation. So you generate the rise phase this way, you generate the fall phase, you multiply them together, you get A of t. You do this for every separate component. And typically then, you would run a separate direct digital synthesis loop. You'd run a direct digital synthesis loop for each separate frequency component, and then multiply the output of the direct digital synthesis by the A of t. So this, yeah, right, sine omega I t. So the DDS for each omega I t is going to give you the sine, direct digital synthesis, and then AI is going to be calculated by finite difference equations. We've got C code that does this. I'll give you some examples here. So this is the best I could do for a Pluck string. Thank you, QuickTime. Does this sound like a Pluck string? Of course, I'm biasing you by telling you what I think it sounds like. It also, it's not a wonderful pluck string, but it's not bad. That's 5 harmonics, and the amplitudes are arranged so that the first the fundamental falls the slowest, and then all the rest of the harmonics are monotonically faster decreasing. They all have a fairly small attack time, so this time is quite short. In this case, for the string, it's about 1/100th of a second, and then the fall times are on the order of a second or so. So what do you think this sounds like? Piano. Let's try it again. Any other opinions?
It doesn't sound like a string to me. It's more like
It doesn't. I'm not saying it should be a string.
it's more like hitting something.
Yeah.
Yeah.
Or some, or marimba, or something with a hollow thing, or something. And in fact, it is designed with using the harmonics from the drum synthesis that used in Lab 3. So frequency 1, the fundamental, is 262 hertz, which is about middle C. And frequency 2 is equal to F1 times 1.58. So it's anharmonic. F3 is equal to 3F1, and F4 is equal to 2.24 times F1. Those are about the dominant. F5 is equal to, what was it, 2.62 times F1. And those correspond to approximately the 5 leading harmonics of the drum simulation you did. Now, I didn't get and the attack time was set as small as I could, because a drum attack time is very fast, but so it's kind of convincing, but not very much. How about this? More like a bell, and really all that is the drum shifted up by a factor of 4. That's the same. F1 is now at 262 times 4, and you get something that is kind of vaguely bell-like. Now, what does this sound like? Some sort of blown thing. You win the big prize. That's what I think it sounds like. Now, in this case, the scheme is to, for a pluck string, let me step back and say the physics is, for a pluck string, you put a lot of energy into it and then you let go. So you have an impulse drive followed by an exponential decay. So for a string, you have this amazingly rapid rise in amplitude followed by an exponential decay. But for a horn resonance system, you're pumping energy slowly into the resonance system. Your breath is a relatively weak driver. And so as you pump in more energy, you get an exponential rise, which is rather slow. In the case of a tuba, I think the exponential rise is on the order of a second. It takes several hundred cycles to drive the horn to full amplitude. And then you have kind of a long fall. But the structure is completely harmonic. That particular note was tuned to 262, and the harmonics, and F2 was twice that, and F3 was 3 times, and F4 was 4 times, and so on. And the amplitudes I picked, and the fall times were picked based on the spectrum of a clarinet I found on the web. So that's why I say you win the big prize. And so you can make something more horn-like by slowing down the attack, more blown instrument type by slowing down the attack. You can make it more impulse-like, string-like by speeding up the attack. And the work required in terms of direct digital synthesis is fairly high. That's 5 harmonics, requires 5 DDS units. Not a big problem on the FPGA. You could put 150 on the FPGA, probably put 1,000 DDS units on the FPGA. So I originally wrote this to run on an 8-bit microcontroller, and 5 DDS units running on the 8-bit microcontroller at 16-bit resolution was beginning to push the processor a little bit. But there's no reason why you couldn't go to more harmonics on an FPGA. But I don't think it's worthwhile going much higher than 10 harmonics, generally. Most of the energy in most signals is in the first few harmonics. FM synthesis, or so-called empirical synthesis, is quite different. There's no particular rational way of designing it. For FM synthesis, the output is going to be given by some A of t, some envelope, some amplitude envelope, which again is going to be more or less exponential rise and fall, times some cosine 2 pi ft plus some other amplitude value. So this is another envelope. So this is another exponential envelope inside the cosine times some sine of 2 pi fm t. What in the world is this? So you have some frequency here which is modulating the phase of the output direct digital synthesis unit. This is a classic FM system. This is of course an amplitude. This is also has sort of units of some weird amplitude, but it's referred to as the depth of the FM modulation. And this is now a frequency at which you are changing the phase of this outer direct digital synthesis unit. This is really hard to visualize what it's going to sound like. And so it's a wonderful way to waste time, because you can say, all right, what will happen if I pick, I don't know, 262 for this rate and 1,000 for this and a depth of 2. Well, what's it, and you can get into situations where the rate is changing so fast here that you have aliasing, and sometimes that makes a cool sound and sometimes it doesn't. So you get all these weird effects. So for instance, This first sound is set to middle C, 262. The FM frequency is 350, and the depth is pretty high. What's it sound like to you? Anybody else have an opinion? It sounds to me like some sort of plate being banged. Yeah, a bell or a plate or something of that sort. Something not particularly nice, but not horrible either. Maybe a lead pipe banging on a steel plate or something. Now if we change the mean frequency to a kilohertz and the FM frequency to 50 hertz. So now this is 1,000 hertz being modulated at a very low frequency. You get something completely different. Which sounds like a stiff rod being plucked or hit or something. It's kind of and that makes sense. Now you have the fairly high frequency here, and you're changing that frequency at a fairly low rate. And you could argue that that's useful. Yeah, there's some weird overtones there. The main frequency there is set to 300, and the FM frequency is set to 1,000. So the phase here is changing 3 times as fast as the phase here, and you're getting all kinds of weird interferences between the two. Depth is pretty high. How about this? Kind of indistinct. Yeah, jaw harp, something kind of. What'd you think? Wait. A what? I don't know that word. Okay. It sounds and.
Something between string
and you know, it sounds like to me is kind of a high-pitched note on a nasty electric guitar. This has some distortion hooked into it. And there's a couple of parameters. There's about 6 parameters. There's a main frequency. There's the rise and fall rate of the main frequency. There's the FM frequency, the FM depth, and the rise and fall rate of the FM modulation. Yeah, I don't know what you use that for. The wobbly saw kind of thing, something with a very low resonant frequency in there someplace, and that's interestingly enough, it's about 300 hertz with 1,000 hertz FM frequency, but it's instead of using a sine wave for the FM, using a triangle wave. And it's probably being, so you just change the direct digital synthesis type from sine to triangle, and it's probably being aliased all over the place, and that's why it has that funny weird sound. And how about this? Who? Bowed string. It sounds to me like some sort of, maybe like a bowed string. Or something. I don't know. It needs work. But fact is, there's C programs and there's MATLAB versions for all this stuff. The MATLAB version, you can just play with all day long. And get to, what's the strangest sound I can get out of this? So much fun. But in some ways, the most interesting to me is physical synthesis. So is it clear how you would implement this on the FPGA? You'd have a direct digital synthesis unit producing this sine wave, DDS unit producing this sine wave. You multiply it by some envelope, and then you apply that phase plus this continuously changing phase to another direct digital synthesis unit that produces this output. So it's two DDS units only, and at the cost of a couple of multiplications instead of instead of 5 DDS units. Any questions? And on all these things, well, direct digital synthesis is very effective at producing a sine wave. There's no reason why you can't change the DDS unit to produce a triangle, a sawtooth, or any other shape waveform that you want to then modulate. And you get separate effects. Physical synthesis takes a different approach. It says what we really want to do is we want to take some partial differential equation, and this should look familiar, except this is the one-dimensional version of the one-dimensional wave equation, which is a subset of course, what you did for Lab 3. And there is a scheme for simplifying this wave equation which works extremely well in one dimension. And that is to note that for the one-dimensional linear wave equation, constant coefficient wave equation, that u of x and t can be represented as the superposition of two time-shifted versions. This is a wave traveling to the right and a wave traveling to the left. That means, now turning it into geometry or turning it into a picture, that means that if you have some string with a wave on it traveling this way, that at some time a little bit later you're going to have the same pulse simply shifted down the string if there's no loss, and perhaps attenuated slightly if there is loss. That means that all you have to do to simulate a string is to have a shift register. And the differential equation is equivalent to a shift register as long as you get the boundary conditions right. And that is that at the ends here, when this hits the end, if it's a fixed end, it gets reflected back, inverted, of course, now traveling this way. So we can solve this partial differential equation by the simple scheme of having some sort of register, some sort of loss element, a register, a loss element, and so on. until we get down to the end of the string. We multiply by -1, and we come back with a register, a loss element, until we get to the end of the string where we have a reflection. So we can then notice the loss elements are all represented as a linear loss, which is to say you're multiplying by some attenuation coefficient, then multiplying the function by a series of losses throughout the loop, and multiplying by -1 twice can all be commuted into one gain. They're all linear operators. Shifts or delays are linear operators. Multiplies by constants are linear operators. That means that this kind of ugly looking loop is equivalent to a shift register. Now we're just going to represent this as an n stage shift register followed by a loss, clumped loss, and fed back to itself. So for the cost of one multiplication per time step and a movement of a pointer, really you don't have to shift everything, you just move the pointer if this is a circular buffer, you can simulate a string, a one-dimensional linear system. This was thought up by two guys, Karplus and Strong. So it's called the Karplus-strong algorithm. Karplus-strong. And the specific form that they took was that you have a shift register that is n samples long, followed by a loss element which was of the form a one sample register with the one sample delayed version of the signal added to itself and then shifted by one and then fed back. So this just takes the average of the two samples coming into it, of the last two samples coming into it, because it adds them together and then divides by 2. It's embarrassingly simple. They were surprised. I don't know quite why they decided to try this, but they were surprised when it sounded exactly like a Pluck string. Because they hadn't thought through the differential equation at the time, I don't think. So this is an example of that. With fairly high damping. The effect of this averaging is to average out the higher harmonics as a function of time. It's a low-pass filter, in fact. And so each of the different frequencies is low-pass filtered with heavier low-pass filtering at higher frequencies. And so it causes string-like dynamics where all higher frequency harmonics die out more quickly than the fundamental. You can load the shift register at t equals 0. You can load the shift register with with some function. If you load it with white noise, it makes a sound like you've plucked a steel string with your fingernail. If you load it with, and that's what this is. But if you use a triangle, you get a softer pluck. And what's this? That's a very, very soft pluck. That's more like a bow. That's actually, yeah. So in that case, what's done is to put an adder here with an outside signal in, and put in a sawtooth. The frequency you get out is proportional to 1 over the length of the shift register. So let's say we have some sample rate, Fs, and we have some length of the shift register. Actually, some frequency we want out, some F naught we want out. Then that will give us the number of delay steps. And if we were to choose, say, 8,000 samples per second and 261.6 hertz, which is middle C, we would find that the length of the shift register has to be 30.58 steps. Oh, that stinks. How do you make a half of a shift register step? Any ideas? Well, it depends on a DSP trick. You make a phase shifter. You make a DSP module that has a phase shift between 0 and 1 sample. So the full karplus-strong, well, I'll talk about that in a minute, but the full karplus-strong then, with everything added, and this is really due to Julius Smith at Stanford, is you have a couple of inputs, as many inputs as you want, which are then added into, and there has to be some, of course, note trigger here, which represents the time, t equals 0 time, which is added into a feedback coming from shift register, which gets shifted out, and in general we're going to have an output filter here. An output filter. And the reason for that is that if you want to use this for something other than a string, let's say a horn, then it turns out that the bell of a horn tends to be a high-pass filter. It tends to output high frequencies better than low frequencies. So we want to be able to have a linear output filter to the outside world. Then we're going to generalize this average, this very low quality loop filter to a more general loop filter, which can be any finite or infinite impulse response filter. And then we need to tune this thing with a all-pass filter, which I have yet to write. So we need a all-pass filter with a phase delay of 0 to 1 sample. And then we may want to put some special effects in here, let's say clipping, so nonlinear effects. Clipping would say that the V in versus V out for clipping might be something like this. And if we add all of those pieces, let's see. So if we put a one-pole filter at the output, high pass, a one-pole filter in the feedback, again, we get something that's kind of horn-like because and that's being driven by a sawtooth waveform, which would be like a reed. A reed lets air through. It's a relaxation oscillator. Bangs shut, lets air through. Bangs shut again. And so you tend to get a sawtooth-like waveform, which is, by the way, what your vocal cords produce also. Although I'm not sure mine today are producing a sawtooth. But we'll see. And oh yeah, if you just take the initial karplus-strong and change this plus to a minus here, you get, did I put this in here someplace? Well, maybe I didn't do that. You get something that sounds like a brass cymbal. It's almost a noise burst, but it sounds very like a brush against a brass cymbal. Cymbal, not the other kind. And the only thing we need to do here is to talk about this all pass. What you do then is you take the output of the shift register, put it through an adder, one sample delay register, another adder to an output, and this is fed forward and multiplied by some eta and added, and this is fed back and multiplied by minus eta and added. And the delay in samples, this is not in hertz, it's in samples, is given by 1 minus eta over 1 plus eta. Or eta is equal to 1 minus delta, the delay, over 1 plus delta. And in terms of doing the arithmetic, y of n then, the output, is equal to x of n minus y of n minus 1 times eta plus x n minus 1. So that's the finite difference equation that you actually implement with this eta, and that's how to calculate eta from the delay that you need. So in the case of where I needed 30.58, I would make my shift register 30 stages long. I would plug in 0.58 here for the delay, calculate the eta, and that would design the all-pass filter necessary to phase shift half of a sample, 0.58 of a sample. So you coarse tune with the number of stages in the shift register, and you fine tune by changing eta. And these filters, the loop filter, can also cause a fractional delay, and so you can either analytically figure it out, or you could tune it by ear, or by Fourier by spectrum analysis of the output. If you have, I can resolve frequencies maybe down to 30%, so I can't tune by ear, but I'll bet some of you can do better than 1%. And then you would tune by ear by doing fractional changes. Any questions? Again, this is just a fabulous way of let me show you one example. Well, let's see what happens, how long this takes to get off the web. Oh, well. This is the first group that used karplus-strong in the microcontroller lab. Slowly it downloads. And you won't be able to see the video, of course, because I didn't bother to hook it up, but you can listen to the, if it ever, I should have preloaded this, I guess. It being a dog here. Ah, there we go. Let me go through to where they're actually playing it.
That's awesome. All right, now I want to come in on the glove a little bit here and take a look.
And this is the output.
Oh, I didn't prepare. Just to look up. All right, again.
Sounds pretty guitar-like. And that's just the simplest karplus-strong algorithm. And this last year, a group did a really very nice virtual guitar and drum set using karplus-strong. What did they call it? It was invisible band.
What you've done here is to build an 8-voice synthesizer. There's four drum voices, one on each stick, and then an accelerometer on each foot, accelerometer on the tips of the drum sticks, and then there a bass drum on one foot. What do you have on the other foot?
Snare.
Okay, and what you got on the sticks? Hi-hat on the stick. Cool. All right, now let's hear the guitar.
And the guy's hitting the hi-hat.
All right.
Just add one more thing.
And what?
Add one more
Okay,
thing.
what's that?
So there are feature.
Oh.
So it was very convincing. They had an accelerometer on each foot, tapping away with each foot, playing the drumsticks, and the other person was playing the imaginary guitar, which had an accelerometer to pluck, and then a kind of virtual fret or a string board in the other hand for choosing strings. So I can talk more about this, but and go through C code as much as you like, but you have to tell me how much you want on this. So let me know if you want to hear more about it. Otherwise, what else do you want to hear about? Or is it time to go into the lab permanently? What do you think? You want to discuss it next time? Okay. Email me about what you want to hear about, and we'll have at least one more lecture.